Welcome back, everybody. Welcome back to the channel. So today we're going to be talking about how to build a code obfuscation system. This is going to be pretty fun, so let's just kind of get right into it. So you're going to need to keep track of two main things. You're going to need to keep track of our module data and our file data. Because as we're compiling our compiler, we're going to be obfuscating both modules and files. Of course, as you guys saw in a previous video I did, we will also be obfuscating classes and fields as well. That's why they had that obfuscation boolean in there. We'll see how to do that shortly. So first we're going to need to create our module data structure. You want to create this basic constructor here where you pass in the name and the serial number. Now here's the basic concept of how my code obfuscation system works. My code obfuscation system is very secure in the sense that it has no attachment to the code it's actually processing. The way that it generates these names, right? So like as you can see here, I have all these various classes in this, executable. If I go up here and I go to type, what is it, -obf, I think. So if I type the obfuscation keyword, we can see here what happens. So a couple of classes actually get kept because I need those on the back end. So like throwable, exception, runtime, or like runtime exception, and others. My virtual machine requires these to be the same names, so these aren't unchanged. But as we can see, all of these classes are completely like they're just arbitrary. And I've looked online for various different algorithms for how to generate names or unique names based on a certain set of parameters for my code obfuscation system. I couldn't find any, so I just made up my own. So I'm pretty proud of it. So it's really cool. We'll see it in a few minutes. But yeah, that's how we basically do it. We base our name generation off of the serial number. So that's why every serial number needs to be different. So each module name or each module data is going to have its own name, serial number, and whether or not we want to obfuscate it. So by default, everything is set to whatever this is set to, right? So if we say -obf, everything in our programming language is by default going to be set to obfuscating to true. That makes the most sense, right? Because we're going to have potentially hundreds of thousands of things that we need to obfuscate. So it would make sense that we just pass in this option here directly, so that way if the user sets it, it just automatically does it. And if they want to basically say that they don't want to obfuscate it, then of course we'll handle that accordingly. Now, there is a specific format for this. So where is that? Is that in here? No, it's in dependencies. So we'll go over how to process this information at a later time. We're not really at a point where we really need to care about this. Honestly, code obfuscation happens at the very end of the compilation cycle, but it is still important we need to build this system because we actually do use it as we're compiling everything, but most of the work happens at the end. So we'll go over the syntax for it later, but you can kind of pause the video and kind of take a look to see how it works. It's very simple. I have two ways of doing it. You can obfuscate modules by passing in the string name, which is basically a module name or a file name. So if you say you want to keep a file, then you can pass that in. If you want to keep a module, you can do that as well. Of course, we also have, here's what's cool about it. All of these are considered U types. So literally, I just hook this into my entire type system, and my compiler already knows how to resolve each of these types. So I just pass in, whatever that code is to the compiler to compile the U type, and it just figures it out. So it's really nice the way I do it. But let's go back to our code obfuscator. The first thing after we create our module data is we're going to need to create, this is the optimizer. We need to create our file data. Files have the same thing. They have a name and a GU ID. And you can see here, this is how you set it up. And of course, they have an obfuscation boolean. After that, we have, and here's my imports, by the way, if any of you guys were wondering. And let's see. So we need to create a obfuscator class. So the first thing we're going to need to do is pass in the compiler. Now, the way that I compile this, or the way that I obfuscate the code, is I do it, like I said, I do this at the very end. Like after we've compiled everything, right when we're about to generate the executable file, I basically pass in the compiler instance here, and then I access things from the compiler instance in this code obfuscator. After that, we have, our destructor. So, once we're done compiling inside of that function, then, and this is the right way to do it. I don't have destructors on a lot of my a lot of my objects because I'm just bad at coding when it comes to destructors, but this one has it, so we just want to free up all of our modules, and yeah. We don't want to free up the files because we're going to need to use the file data right as we're generating our executable, so we don't free up that data. So we have, all right, so let's get right into the algorithm. So here's going to be like, we're going to do the fun part and then the boring stuff later. So first, we're going to basically need to have an alphabet count. Now, here's how it works. We pass in an ID, and based on that unique ID, whatever it is, we basically generate a string of characters. Now, the way that it's supposed to work, it's supposed to generate characters ascending based on like from A to Z. So what that means is, so here, if I put a comment, let me do this. So as it's generating, it's going to say A, B, C, D, all the way to Z. But then once we get past Z, it says AA, AB, AC, so on and so forth. You guys get the point. So that's kind of how the algorithm works. And we basically create an alphabet of every single character. We have a max buffer size of 32. Now, here's what's really amazing about the algorithm I made. We will never have more than 32 words in our actual name. And what's mind-blowing about this is no matter what number you pass, so we can pass a number from 1 all the way to 9 quadrillion, like the highest number that a 64-bit computer can process, and each word will all be unique. It's really cool. So let's see how I do it. So I basically create a buffer, and I have a max buffer size. I have a result buffer, and there's a reason for that. When we generate the buffer, or when we generate the name, it's going to be backwards. So when I generate the name, it's going to come out as, A, B, C, D. That's fine, right? But let's say we get to AA, then AB. Well, AA, you can't really recognize it, but we have a result buffer because once I generate the name from the algorithm that I'm going to show you below, it starts out as BA. So it starts out backwards, and then we have to basically flip it. So if we have a character called ABC, it would start out as CBA. Why did that not? Oh, I guess my computer's frozen. Yeah, so it would be CBA, and that's how it would be printed out. So we just need to like basically flip the buffer to print out the appropriate name. So we're going to create a list of modules and a list of files. This is just a static version because these are static fields. So we want to create those. Now let's get down to the name generation. So what we need to do is we basically pass in an ID, and if the ID is less than 0, we return an invalid, or we do an invalid ID. We just throw an exception, say cannot obfuscate invalid ID of blank. This should never happen. This has happened to me before in my compiler, but I fixed all of those bugs. I've been fixing tons of bugs. It's just a failsafe. It really should never happen. So the way the algorithm works is for any ID less than the alphabet count, right? So basically if the ID is less than 26, which is how many characters we have in the alphabet, then we return, that letter, right? Because that's obviously pretty easy. But here's where it gets interesting. So we create what's called a string size. This is going to be the size of our buffer, and that's going to be the size of the name. And what we do is we just say while ID is greater than 0, so we're going to be modifying this integer here. So we're going to say if string size is less than the max buffer size, so of course we should never go over 32, and I'm actually going to prove to you based on the math why we will never have more than 32 characters, but let's just kind of look to see what happens first before we get into that. So we're going to create a letter index, and we want to get the index of the first letter. So we take the ID. So if we have like, I don't know, 26, right, and we percent alphabet count. So if we do 26, let's do this on Google. So we say 26 percent 26, that's going to give you 0. And 0 gives you A, right? So we have A, and then we basically want to do some simple math here. So we need to do this. Why did I put a note here? Let me see what it says. We need to do this, so we start after ID of 26. Yeah, okay, so There's some weird, there's a legitimate reason why we want to do this. There's some wording issues with the letter index. So if the letter index is equal to 0, we want to say AAAB. Otherwise, it's going to come out malformed. So we basically want to check to see if the letter index is 0. If so, we return Z, which is alphabet count minus 1. Otherwise, we return letter index minus 1. So whatever the letter index is, whatever character we're at minus 1. And then we basically have a buffer of string size, and we increment the string size, or we get the value and then we increment it because of course we're creating a string, so it needs to go up in size. And we basically get the alphabet at the letter's index. And then here's where the magic happens. So then we say alphabet count, or ID, divided by alphabet count. So every time we process a letter, we divide it by 26. And here is the proof in why we will never have more than 32 characters. So I'm going to do this. Now, even though my language is built for 32-bit operating systems, I definitely have the ability to generate some pretty large names based on, if we have a 64-bit PC, then of course, the names can go even higher. But let's do this. So if I go here and I enable basically every single bit, and I do that, let's say we have the largest number possible that a 64-bit PC can process. Obviously, it's not like this can double, because if we had a uint 32 or uint 64, then obviously this number would be bigger, but that's not the point. What I'm going to do is I'm going to divide by 26, and we're going to see how many times do we divide by 26 until we get to 0. So divide by 26, divide by 26, and let's just kind of keep doing this. Oops, okay, I screwed that up. That is an epic fail. I'm going to be back, and once I divide it correctly, we can see what the result is. All right, so I'm back. So we're at a point now where I've divided it down to 3. So if I do divide by 26 one more time, we get 0. So, and of course, I check to see if it's greater than 0. So if it's equal to 0, obviously 0 is not greater than 0, so it's going to break out this while loop. So let's see how many characters the largest number that a 64-bit PC could potentially process. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So even at the largest value, we cannot process more than 14 characters for a 64-bit PC. We're processing integers or signed ints, so we're doing an N64, not an unsigned int. So that basically guarantees that we will not have more than 32 characters. Also, by the way, it's extremely low odds that they're going to have any ID over a billion, because, I mean, you'd have to have a really big program to do that anyway. So, yeah, we don't really have to worry about that too much. And of course, like I said, it'll throw an error and our compiler will catch it and they'll get a message, and it'll be an internal error because obviously I'm not processing more than the maximum value that we can process. So yeah, we don't have to worry about it. Otherwise, we have, so this should never happen, but if, the string size is greater than the max buffer size, we just put a question mark and we set string size to 1. Finally, we flip the buffer. So what we do is we basically start at the end. So we start at string size minus 1. We say, I is greater than 0, and we minus I, and we just basically go backwards from the end of the buffer to the first part of the buffer, or we flip the value to be what we want it to be. Finally, we return string, and that's it. And as you can see here, we have like this clear buffer. Where is this being used? Yeah, so we have this clear buffer function that just goes through for max buffer, and it just sets all the values to 0. So I'm pretty sure some of you are wondering, well, that's cool and all, but how do you know this actually works? I've thought about that, and I have a check reliability function. So we're going to see a couple things with this function. First of all, before we do anything, we're going to see how this code generator works, how this algorithm works to generate names. And then we're going to run a test. We're going to run a test. Now, I have a max sample size of 100,000 strings because that's a lot of processing, and it actually takes a really long time to process this. It probably takes about at least 2 minutes to 3 minutes to process 100,000 strings, even in C++, because you have to not only do 100,000 for loops, but you have to do for loops within inside of each string. So it extrapolates out to be a pretty massive amount of computation. So I'm actually going to go here. So we're going to start off simple, and I'm going to see out the name. So let's say ID is equal to, and we say start, S-T-A-R-T, start ID minus 1, because obviously we've incremented here, so we want to just get the appropriate ID. So that way we can kind of see what's the value that we're processing. And let's say name is equal to, and let's say name at string size minus 1, because again, of course, we're incrementing string size. Let's put a new line here, and I forgot to .str. Yeah. All right, so let's call this function. So check reliability. So I'm going to go to my compiler here, and we can actually see this in work. So instead of calling obfuscator, here, I'll just do this, obf.check reliability, and let's go up to 10. Let's just start very simple, or no, we can actually have a higher number. Let's do up to 30. So we can actually see the algorithm in action even after we pass the max value of 26. So we have, what do we need? Do we pass anything else in? Oh yeah, the sample size. Okay, so we start at index of 0 and the sample size is 30. So we're going to sample 30 different strings, and we can actually see what they print out. So here, I'm going to hit play, and I'll be back once this compiles and we can see the result. All right, so we have the result here, and the compiler is fully compiled, and we can see here we started an ID of 0, A, B, C, D, E, F, G, blah, blah, blah. And as you can see, we go all the way up to 25, index of 25. And now here's the thing, my algorithm is not perfect. So it doesn't perfectly generate correct names. So it starts out as AZ, and then it goes to AA, AB, AC for each number. But the point is that the algorithm is always going to be unique. So as we can see, so here, I'll do a bigger sample size. Let's say 100. So let's rerun it, and we'll get a printout of 100 different characters to kind of see, the various generation. And then after that, we'll just go wild and go nuts and see if it's actually reliable. So as you can see here, if I scroll down slowly, you can kind of see every single name is unique. And we go all the way through the alphabet. So we started AA, and we go all the way to AY. And then we start at BZ. Then we go from BA all the way to BY. And then CZ, and you can kind of see it. You get the point. So let's go back to check reliability, and I'm going to remove this. Now we can see here that it returns a Boolean. And what this function does is it generates a bunch of names. It for loops through every single name. So if you have 100,000 sample size, it's going to for loop all 100,000 samples. It's going to get that name, and then it's going to for loop through the entire list again to see if it finds that same name inside of the list. Now, obviously, it's going to find it at least one time because it is present at least one time in this list. So we have what's called a count, and we basically just say count is equal to 0. If we find it, we basically check to see if count is greater than 1. If so, that means we have more than one copy of this name. We should only have one copy of the actual string. So if so, then we return false. Otherwise, we just increment count, and we return true or false based on whether or not it exists more than one time in the entire list. So let's go back. So I'm going to go to compiler. Now, oops, I made a mistake. So now I'm going to do a check. So I'm going to say, so if it's false, that means it's not reliable. So I'm going to say if this cout, oops, cout, then we can say we did not find any multiple copies of each word. You know what? That's actually too long. I'm going to just say we are reliable. Otherwise, if it's false, then we want to say we are not reliable. So I'm going to just print out in big letters, say error, we are not not reliable. And if this returns false, that means that we're not reliable. So let's just kind of do, again, just a proof of concept to see what this function returns. Obviously, we saw with 100 characters, it was pretty reliable. So yeah, so we are reliable. So that's good. So now let's go all the way up to 100,000. So from 0 all the way up to 100 grand, we're going to say, we're going to do a check to basically verify that there are no copies inside of this function. So to actually, I'm just going to let it run. Hopefully it's not too long. I'm actually just going to not edit this out and see how long it's actually going to take. Um, Hopefully it shouldn't take too long. I have no idea how long it's going to take though. But after this, we really don't have to do 100,000. We can just kind of do like, I don't know, 30,000 or maybe not even like 20,000. I think 20,000 is a lot. So if we sample over 20,000 strings, we can basically guarantee that there's no copies in there. And we can just run it a lot more times and test various different numbers. So that way we're not like sitting here, as you can see, it takes an extremely long time, and I have an i7 chip on my computer, so it's even running in C++, it's taking a while. I guess I wasn't at the best performance, but even still, it's taking forever. Oh man. Okay, all right, there we go. So we got it back. It took a really long time. That's ridiculous, but as you can see, we're reliable. So we went across 100,000 strings generated from 0 to 100K. And again, like if you remember, we start at a certain ID and we just plus it. So that's from 0 to 100K and it's all good. Now, I know you're thinking like, okay, well, what about high numbers? So I'm just going to do this. I'm just going to type in what did I break something? Oh, okay. So I'm going to type in a stupid number. What is this? This is like 949 million. So it's 30 billion 949 million. So we're going to run a test again. And yeah, okay, so 20,000 was actually not that bad. And we can see we're still reliable. So let's do another one. Let's do another test. Say 9. I'm just gonna put a bunch of 9s. Can I do that? Is that a legal number? Yep. All right. So I just got like this huge number here, and I mean, at this point, I think you guys get it. Like it's pretty reliable. You're not gonna have any issues with this code. So once we check this last one, then we can just kind of continue on so that way we can finish this episode. I don't want it to be too long. How long is this video? All right, so we're reliable still, so it's pretty good. So let's go back and all right, so let's just kind of go down the list and like look at all the various functions that we have. So first, you're going to need to be able to find a package. This is a function that basically takes a module data pointer and it takes a void pointer. Now this is for my list class that I created. This is just a quick function to find a package based on, passing in the actual data and checking to see if the names are the same. We also have a find file, so you can just copy these two functions down. So we have that, and then next after that, we need to basically obfuscate the code. So this is how we obfuscate a class. So we check to see if the class is obfuscatable. So basically the way it's going to work is if we say we want to keep a class, we're going to keep everything in that class. We're not going to like obfuscate anything in that class. If you say you want to keep a class, everything in it is going to get kept. If you say you want to keep specific portions of it, then those portions will get obfuscated. So it's not perfect, but that's just what I have. So we check to see if the class is generic. Now, what this does, we'll go over that later. But this is just a bit shift where we basically look at the class type and we pass in the class type, which is an integer, which you guys saw yesterday. And we check to see if it's a generic class based on whether or not that bit is active. I'll go over that bit shifting in a later episode. But yeah, so if we have a generic class and the generic owner is equal to null, then we return. Now, the reason why you want to do that is if the generic owner is equal to null, that means that this is in fact the signature of the original generic class that we compiled in our compiler. So we don't want to do that. We only want to do it for legit classes because legit classes are the only ones that are going to be put out into the executable. So we basically pass in the serial number of the class. And this is why this code obfuscation framework is so secure, because this is completely random. Like it's completely by chance that we somehow compiled this class and it got this random ID. This isn't like addresses. Addresses are typically pretty stable between builds, but like GU IDs are completely random. It is completely dependent on when the compiler decides to process a certain amount of information. So we just, call this function out we just went over, and we get the value and set that as a name. Then we obfuscate the full name. The way we do that is we basically check to see if the owner of the class is equal to null. So if this class has no owner, and you guys remember ownership versus inheritance. So if this class has no owner, then what we do is we say module data, and we get the package. So, we get the actual module pointer, which references the pointer inside of our list here of modules, which is really good. So that's very easy. It's just a way to save memory. We check to see if the package wants to be obfuscated. If so, then we basically create a full name by obfuscating the package by passing in the serial number of the package, hashtag, and then we pass in the serial number of whatever data entity we're passing in. So if you remember, data entities are everything. It's fields, classes, functions, whatever. So that's why I just pass in the pointer, and we have all the basic information inside of data entity to be able to perfectly obfuscate what we want. So we do that for whether or not we want to obfuscate a package name. Otherwise, if we don't want to obfuscate the package name, then we just pass in the package name to create the full name. We pass in just whatever the value is, hashtag, and then we basically generate the name based on the serial number. So otherwise we have, so if the owner is not equal to null, then that means that maybe it's like a subclass or something like that. So we generate a full name by getting the owner's full name, and then we say dot, and then we generate the name based on the serial number here. Let's go back. So we're at obfuscate full name. And after that, we have, so we for loop through all of our classes, right? So we're going to for loop through all of our fields, and we want to just basically say get field at index, whatever, and obfuscate. And that's literally it. We do this for functions, same thing. We do this for child classes, same thing. Now, this is going to actually call this function, and it's just going to recursively come back in here. You want to use recursion because what if this subclass has other subclasses in it, and what if the subclasses after that also have subclasses? You want to just do that so that way you can just process all the information. So we have all of that. We went over obfuscate, went over this one. Now we want to generate a mapping file. Now this mapping file is going to basically be the file that another program is going to use to reference our executable. So I haven't done it yet, but I'm planning on building a console application. It's going to start out as a console application, and then eventually it'll become a GUI. But basically, it's going to be an application where we can pass it the mapping file. So here's our mapping file. Why didn't it open? So here's going to be how our mapping file looks. And we're basically going to pass it this mapping file. And then we're also going to pass it the executable we want to try to deobfuscate. And it's going to attempt to take this mapping file and deobfuscate the executable that we pass in and spit out the executable on the other end with it being deobfuscated. So that's kind of the tool that we're going to use. And obfuscation, it has a purpose, right? Like if you want to secure your code, well, then you don't want to have the virtual machine try to deobfuscate it. Like this mapping file is not going to be used by our virtual machine. Number one, that's slow, and number two, that defeats the purpose of code obfuscation. So as you can see here, we have packages, we have our files, we have our classes, fields, so on and so forth. So this is just a basic mapping file. It just has like what is the thing we're trying to obfuscate equals, and then what turns out to be the value. And as you can see here, like if I do a find right now, if I try to search for this character, again, there's no copies because my algorithm for generating these names, it's completely unique. So we don't have to worry about there being copies for anything. If we go back to our code optimizer, our code obfuscator, we go back to generate mapping file. So now what we want to do is we want to say create dump file for whatever. So I'm actually going to just pull it side to side so we can kind of see what is being generated as we're going through the code. So we're going to start out by printing out this message, and the reason why we want to do this is because like as the programmer or as the developer, we want to be able to, if someone's programming in our language and they're looking for mapping files, we want to put the name of the executable that this mapping file represents. Now, I will make something very clear. Mapping files change from build to build. I basically made trying to figure out and reverse engineering my code nearly impossible. Now, you can still do it, but you won't have any concept of knowing what each class, field, or function is and or what it's doing. So it's going to be very difficult to do that. And actually, if I hit play, we can actually see that the file changes every single build. So every time you hit play and you rebuild the application, literally everything changes. So it will never be the same names as it was before. That's the whole point of code obfuscation, and it's really secure. It's really cool. And as you can see, the things that we keep says no change. So we want to print out packages. So we want to start out with that first. We just loop through our modules, say what is the name equals, and whether or not we obfuscated it. If we obfuscated it, we generate the name based on the serial number. Otherwise, we say no change. And as you can see, we keep std because we need the standard library to stay in our executable because the virtual machine requires that. And we say no change there. After that, we have files. We do the same thing. For loop through the files, get a file, print out the name equals, check to see if it obfuscates, and put the name or generate the name based on its serial number. Otherwise, say no change. Same thing with classes. So for classes, we basically print a class mapping. So we put the brackets here for classes, and then we for loop through all the classes, get a class, call print class mapping. All this does is we pass in the string stream of as we're building this file or this mapping file. We say, here's the class name, the full name. Full name is very important because you could have multiple classes and multiple libraries or multiple modules and they could share the same name. So we want to put the full name equals, check to see if we want to obfuscate and either print the generated name or no change. And then if we have any child classes, we want to print the class mapping for those. So we do that for classes. Then if we go back, so after that we have fields. So we print out all of our fields in our language or in our executable, and we for loop through the classes, get the class, and print class field mapping. Same thing, we just get the full name equals and then same code as before. Now, here's what's different though. I check to see if the field owner is obfuscating because right now what I'm doing is I'm just for looping through all the classes and printing out the fields. But if you remember, we'll only obfuscate a class if the class itself is allowing us to obfuscate it. If it doesn't, then anything inside of that class will not be obfuscated. So we just want to make absolutely sure that the owner says, okay, it's okay to obfuscate, and the field also wants to be obfuscated. And if both of those are true, we print out the generated name, otherwise no change. And then we just for loop through all the child classes and call the same function. After that, what else? So we have that. We have methods. So now we're down to here. We have our methods. Oh, I guess I passed it. Yeah, so we have our methods and we for loop through all the classes, print class method. It's the same stuff, guys. Like, I don't think I have to go over it, but it's literally the same. We do the same thing like we did for fields where we check the owner to make sure that it wants to be obfuscated as well. And we do what we need to do. So that's going to be it. So after that, we just write the file out. So we just basically say file.write. This is the file class that I created. That is located in my util. So if you guys want to copy that code down, it's in my lib. So it's in my lib directory, and then util, and then file.h. And you can like create a buffer here and stuff, and like you can do stuff. So like you can read all the data from a file, you can write data to a file, check whether it's empty, it exists, other stuff as well. So that's going to be it. And also field or file.c++ is here as well. But yeah, so that's everything for, oh, I guess there's one more thing. Yeah, so we have to basically add and get modules. So as we're processing code in our compiler, we're going to be creating modules, right? Because every time we have a new file, we need to have a module at the top. So if there's a new module, we want to be able to get that module, we want to be able to add it, we want to also be able to get and add files. So the way we do it is I create a data structure called package. It's just a temporary data structure. We pass in the name. We don't need to give it a GU ID because that's not how we process it. Get the index of that actual pointer of that module. And basically we say module index of, and we pass it the find package function. And all that does is, it just calls this function pointer and it checks to see, do we have this element here? And then it returns I. But yeah, so that's in my list class, and we pass it the reference to the package variable that we want to check for. And again, it just checks for the name. So that's how it works. And if index is -1, which of course, if it doesn't find it, then it'll return -1. We return null, otherwise we return the module at the index, because if you remember, it's a pointer. So we're just gonna return that pointer. And yeah, so we have that. Also, we have add module. So if get module is equal to null, then we want to add a new module. This is how we pass in the pointer. We pass in a name and an ID. Also, we have, I guess, our GU IDs UINts. Interesting. I might need to change that in my code obfuscator. So when I'm actually generating the names, I can put it to a UINT, but whatever, I'll do that later. Not really a big deal. So after that, we have get file, we pass it a name, same stuff. It's the exact same code, except we call find file, because obviously it's a different data structure. Yeah, so we have that, and add file, same stuff. You just get a file, if it's null, add it as a pointer. That's it. So that's going to be it for today, guys. As usual, if you have any questions, definitely put them in the comment section below. But we're making some traction. So we have gone through quite a lot. We've finished the entire object-oriented folder, the entire code obfuscation folder, the entire data folder, and tomorrow we're going to be talking about how to generate or how to build a code holder. Once we do that, we're good to go. All we have literally is just these 5 files, or these like 6 or 7 files here, and we're done. Like that's the entire compiler. Now I know that seems easy, but remember, this is like almost 10,000 lines of code. So there's lots of stuff to do. But yeah, so, and of course, if you guys would love to help support the channel, definitely head over to my GitHub repository at androidevcd/sharp. When you do, definitely watch, start, and fork this repository. That's going to give this repository a lot more visibility and let other developers know this language exists. Also, if you guys are curious about learning what I've been up to on a daily basis, you can head over to the remastered branch, and I write some pretty wordy commits, so you can kind of get a gist of what I've been up to without really having to look in the code. Also, if you're curious about learning maybe some of the things that I'm looking to add in the future or stuff I've done in the past, you can head over to the doc folder in the remastered branch. And there's 2 main files. You can check out the change list. That's pretty much everything that I've done as far as past releases go in terms of updates. And the roadmap file is pretty much everything not only have I done in the past, but also stuff I'm looking to add in the future. Definitely recommend checking out this file. It's updated regularly and it gives you a pretty good insight into the language itself. So that's going to be it for today, guys. As usual, if you're new to the channel, definitely consider subscribing, and until next time, I'll see you guys later.